Swayam Prabha. Digital India. Educated India.
We continue our discussion on characteristics form of one-dimensional Euler equation in this lecture. So, in the last lecture we had come up with this form of Euler equation, and you recall that this was written with the idea of converting the equations from the conserved variables u to the characteristic variables v space. And the interesting part is that we now have a coefficient matrix here which is diagonal. So, this gives a wave form to the system of equations. Why is it? Because as you can see that if you look at any ith component of this system of equations, so the system of equations is this, it has multiple components. So, if you are looking at any ith component, it can be written like this, which is like very similar to the linear advection equation in terms of structure, right. So, you have a certain speed lambda which is playing an analogous role to A in linear advection equation, and different components can have different contributions. So, lambda 1, lambda 2, lambda 3 may have different values. So, in linear advection equation, because it was only one equation, a scalar conservation law, we had only one speed. Here we will have multiple speeds coming from the multiple lambdas, but in principle the different components can be individually represented like linear advection equation. So, that gives it a very clear wave form. So, characteristic form of the equations very explicitly show us the wave form of a hyperbolic system of partial differential equations. Now, there is a slight issue over here in terms of how these lambdas behave. So, since we are handling nonlinear partial differential equations, these lambdas would depend on all the characteristic variables. That means, if you pick any lambda I, it will depend on all the characteristic variables, say V 1, V 2, V 3 and so on. It does not have its dependence only on the respective characteristic variable. That means, we cannot say that lambda I is only dependent on V I. It will be influenced by other V's also. So, that is a distinct issue in nonlinear partial differential equations or even quasi-linear hyperbolic partial differential equations. But apart from that, the analysis is very similar. That means, if we look back at the concept of characteristics that we were discussing in some of the previous lectures, that the V I, the characteristic variable, will remain constant, and as long as you are moving along a certain characteristic which is defined by dx dt equal to lambda I. So, let us see where we stand at this point. So, we had shown how the vector model equation can be expressed from the conservative form to the non-conservative form involving the Jacobian matrix. This should be lower case, and then we showed how to obtain the different entries of the Jacobian matrix A. We discussed about the diagonalization property of matrix A, which makes it a hyperbolic system, and then we were talking about Q and Q inverse comprising of the right and left eigenvectors of A. They are dependent on A, and then if you obtain the characteristic form from the conservation form of Euler equation, you can show that the capital lambda matrix, which is the diagonal matrix on the right hand side of this equation, takes up this form. We are not going into the details of the calculation, but this is available in many more elaborate texts on the subject. We are just trying to obtain the information straight away and state it here. So, we find that the entries in the diagonal matrix are u, u plus 1 and u minus u, u plus a and u minus a. So, you can call them as lambda 1, lambda 2, lambda 3. So, like we were saying before, in the case of linear advection equation, the lambda was equal to a. In the case of inviscid Burger's equation, the lambda was u, and in the case of Euler equation in one dimension, we have multiple lambdas because it is a vector model, and they happen to be u, u plus a and u minus a. That means, we can expect that information through the domain will percolate at different speeds along different characteristic directions. So, that brings us closer to a physical interpretation of Euler equation. So, there is apparently a very elegant connection between the flow physics and the mathematics of characteristics. So, if you consider the characteristic family and take the different components into picture. So, the first value of lambda, the wave speed, lambda 1 is equal to u. Now, that creates wave fronts which are defined by this equation. So, u is equal to dx dt. From there we can define these wave fronts, the equations of these wave fronts, and they are nothing but the path lines of the flow, which comes from our basic fluid mechanics, which means that the first family of waves, they would travel along with the fluid. And what information or signal do they propagate? They are supposed to be propagating entropy information. So, they are called as entropy waves. We mentioned about it earlier in a previous lecture on Euler equation, but now we come up with a more concrete information that how or where from this entropy wave emerges. So, it comes from the first component of the lambda vector or lambda matrix. And now, if you look at the other two families of characteristics, we find that their wave fronts will satisfy these equations. The one will be dx equal to u plus a times bt, another will be dx equal to u minus a into dt. Now, if it is u plus a, it corresponds to travelling at the local flow speed plus the local speed of sound. So, your local flow speed, if you add the speed of sound to that, there is a wave front propagating at that speed. And there is another wave front which along which if you travel, you are going to travel at the local flow speed minus the local speed of sound. So, it is wave speeds which are traveling at the speed of sound relative to the flow in two different directions. You can look at it that way, and these waves are called as the acoustic waves. And incidentally, though we understand the concept of acoustic waves, the signal that is propagated along an acoustic wave is not very easy to describe. We can just stop by saying that these are acoustic waves, and we know at what speeds they propagate. Now, let us try to make a small sketch to take it forward further. So, we make a small x-t diagram for Euler equation like we have been doing for the previous scalar conservation laws, and we find that if we take any point x t in that plane, then there are three characteristic lines which will or characteristic curves which will pass through that point x t, and each one of them will have a separate slope. So, if you look at the 3, you have one carrying information dx dt equal to u, another carrying information the slope equal to u plus a, another is u minus a. And what happens is that because there are nonlinear interactions, like we were saying that the lambda i's are not dependent on only v i's, but all the different v's. So, these nonlinear interactions between the 3 characteristics make them curved. However, you can reduce or eliminate them if one or two characteristic variables become constant. So, we are talking about those v i's, the characteristic variables. So, if one or two characteristic variables are constant, then you will see that these characteristic lines will become straight lines, and then we have the so called simple waves formed. So, it depends on how the characteristic variables are behaving in a certain region of the flow. Depending on that, these characteristic curves, the nature of these curves will change. So, in general, due to these nonlinear interactions, they will be curved. Now, of course, if you look at this point x t, we will always be able to define a domain of dependence and a range of influence for this point x t. So, information propagates into the point from here and out of the point into this region. So, accordingly those domains get defined. Now, if you consider different kinds of flow speeds, that means you are now trying to define u and its direction. So, you can have the value of u being less than or greater than a, and again it is the direction of u, whether it is moving towards the positive x direction or negative x direction. Accordingly, the characteristic slopes will be decided. So, let us say if there is a supersonic flow moving from say left to the right, what will that do to all these characteristics? What you will see is it makes all the waves to travel in one direction. It forces to sweep them towards its flow direction. So, all the waves are swept downward and none can travel upward or upwind rather. Now, when that happens, there is a very interesting thing which will occur. If you are standing at a point like this, what will happen is, if there is a noise source upstream of you, then you will hear the noise source. But if you create a noise at your point, you will never be heard by that location from where the other noise is coming. So, this is not possible. So, there is only one directional signal propagation which is possible. Now, if you think that supersonic flow is traveling in the negative x direction, again all the waves will sweep towards the negative direction. But the physics remains very similar in nature, what we discussed regarding the system of waves when the supersonic flow is moving towards the positive x direction. Only the directions just become opposite. Now, the things are slightly more difficult, more involved when it is subsonic flow. The moment it is subsonic flow, you have to remember that if you look at these values, then these values will remain positive as long as you are moving along the positive x direction, and remember that your u is less than a, because you are subsonic, your Mach number is less than 1. Now, what will happen to this? This will become less than 0. So, naturally two waves will slope along the flow direction, while one will slope the other direction. So, that is what happens when you have a subsonic flow traveling in the positive x direction. So, two waves speeds are positive, one wave speed is negative, and accordingly their slopes. Again, similar things will happen when there is a subsonic flow proceeding towards the negative x direction. So, you have to think for yourself how it behaves in that case, how the wave speeds will, their signs will be decided, how the slopes will be decided. When it comes to very low subsonic flow, where the compressibility effect is now lost altogether, that means disturbances can propagate at infinite speeds into the domain. The sonic speed limits to infinity. Then what will happen? What we have mentioned over here in the last bullet point, the wave speeds are assumed to be infinite, and then all regions of the fluid can communicate with all other regions of the fluid instantly, and the domain of dependence and range of influence equal the entire fluid. So, there are no regions specifically defined which will just be able to communicate or not communicate. Every part of the domain will communicate with every other part. So, that is how incompressible flows will behave. So, now we are able to connect things together from a more global perspective, which this wave concept has brought about. Now, we will start looking at some of the numerical methods for Euler equations. We will first look at an approach called as the flux approach, which is a comparatively simpler approach. In fact, one of the simplest approaches for application of either scalar conservation laws or vector laws like Euler equations. So, we look at the derivative definition using CD2 scheme using a scalar flux f in this first equation, which is a very routine equation we have seen in our finite difference exercises, and we just apply it to a vector f. The law remains identically the same. If you try to do numerical integrations like which you need for say finite volume approaches, the rules also remain the same there. So, that means the regular rules which we have seen applicable for scalars are extendable to vectors in this manner, and that is the basis on which the different terms would be discretized in the vector model problem. So, what you are doing is simply replacing the scalar u by the vector u, the scalar f by the vector f, and the scalar derivative a df du, where f is a scalar, u is also a scalar, by a Jacobian matrix. So, that is the only big difference which is coming up, but functionally it looks very similar. So, this is how the flux approach calculations are essentially done. We will just try to elaborate on it and look at a few schemes in this domain, some of which we have already studied earlier. So, the Lax-Friedrichs method, when it is applied to Euler equation, would take up a form like this. A good exercise to do at home would be to try deriving this form yourself, because you are aware of the Lax-Friedrichs method as applicable to scalar conservation laws, especially linear advection equation. Now, from our prior experience we know it exhibits considerable smearing and dissipation. That is one property. The other is that it has 2 point odd even plateaus. This is because of the decoupling issue, and as you can understand that from the stencil itself, it is clear that you have I plus 1, I minus 1 influencing I, and that is where from this whole problem arises. And then you have the issue that the large amount of dissipation because of the first order accuracy. If you go to second order methods, you look at the Lax-Wendorf methods. Here you can find that the Jacobian matrix comes into the calculation. That means you have a matrix getting multiplied with a vector. That usually makes the computational scheme quite costly, because you have large number of components repeatedly to be multiplied. So, every evaluation of AU is also expensive, because as you can notice that in this scheme we have used 2 grids. One is the main grid comprising of i's and I plus 1s. There is also a staggered location at which you are calculating the Jacobian matrix. So, one thing is you have to evaluate the Jacobian matrix at the staggered locations. The other is that you also want to do the matrix vector multiplications. So, both of this can make this scheme quite expensive. There are numerous ways in which you can calculate this value of the Jacobian matrix at staggered locations. We have seen a very simple one has been shown over here. This is one of the simplest possible ways. There are more better and more accurate ways of doing it by examples like row averaging, but we are not discussing that here. So, second order methods of this kind would have better accuracy, but will suffer from higher computational costs. Moreover, there may be issues of numerical oscillations which has to be tackled very carefully and damped carefully, so that we do not lead the calculations to become completely unstable. Now, forming the average Jacobian matrices and carrying out these vector matrix multiplications can add to the expenses significantly, and they can go to an extent where Lax-Wendorf method can become uncompetitive with other methods. So, in order to keep it competitive still, certain other variants have been evolved over time, and one of the more popular variant is the Rich-Meyer method, which is shown over here. It is essentially a two-step method. So, these variants of the basic Lax-Wendorf scheme are essentially two-step schemes, and they are somehow able to tackle this problem of eliminating the Jacobian matrix out of the calculation and therefore making it less costly, and thereby even the matrix vector multiplications are also eliminated. So, we generally say that such stepped schemes are comprised of a predictor step and a corrector step. So, predictor step gives us certain prediction about the vector u, and then we try to correct it before we take it to the next time step. So, essentially you are taking the solution from n to n plus half through a prediction, and then from n plus half, that is at the prediction level, to the corrected velocity, or rather the corrected vector u at the next time step n plus 1. So, that is how the whole setup works. So, in the first predictor step, as you can see, it is a Lax-Friedrichs method which has been applied, and in the corrector step it is the leapfrog method which has been applied. This is somewhat analogous to the two-step Runge-Kutta type of methods which we are aware of in the context of solving ordinary differential equations. And even in the case of Rich-Meyer method, you can see that there are two grids which have been used. One is the standard grid, the other is the staggered grid. The interesting thing is that the predictor maps the standard grid to the staggered grid, and the corrector step maps the staggered grid back to the standard grid. So, these kind of back and forth between standard and staggered grids also sometimes add to the numerical robustness of schemes. Very often we find the use of both standard as well as staggered grid schemes in these predictor corrector kind of methods. Another very widely used and popular predictor corrector based method which has been around for a long time in solving Euler equations is the Lax-Wendorf method, modified version known as McCormack's method. So, it is again a predictor corrector version of the Lax-Wendorf method which is known as McCormack's method. So, here once again you find that there is a predictor step and a corrector step, and the predictor step values are usually represented by overbar, and the corrector step values are of course represented by the next time step value. So, once again you are going from the nth time step values to the predictor values which are indicated by an overbar, and the overbar field taken to the corrector step which is the n plus 1th time step. Incidentally, McCormack does not use a mix of staggered and standard grid. It works on the standard grid alone, but you need to notice that in the predictor step, when you are taking a difference of the fluxes, you are using the grid points I plus 1 and I, while in the corrector step you are taking the grid points I and I minus 1. So, you can imagine that waves which are travelling from right to the left will be better tackled in this step, waves which are travelling from left to the right will be tackled better with the second step. So, that way with the mixing and matching, it manages to capture different kinds of waves which are possible in a given flow field through the change in the direction or the bias in the stencil. Now, usually Lax-Wendorf based solvers add artificial viscosity in some manner. Now, for example, the Richmond method, it uses constant coefficient second order artificial viscosity, which is represented by a term like this or an expression like this. So, as you can see, it is applied in the corrector step. So, this artificial viscosity would help tackle the nonlinear instabilities which may occur due to the discontinuities which form in the flow field as computations go on, which is due to either shock wave or contact discontinuity. So, we have discussed a few methods under the umbrella of flux approach. Remember that in the flux approach we never talked about the wave aspect of the problem. So, there is another set of schemes or approaches which can broadly be covered under the wave approach, which we will discuss subsequently. Before we do that, we introduce the shock tube problem, where we have a long tube which is usually a thick metallic tube, inside which we initially have a diaphragm, that means a physical wall. It is usually not too thick a wall, it should be breakable by some means, mechanical or electrical means, at a point of time precisely where you would like it to break, and then you try to look at how the shock tube operates. Now, what we need to understand is that when the wall exists, then across the wall what is that we have. So, we usually have two gases, or it could be the same gas, but at different pressure, or could be even different density, could be even different temperature, and then once we break the wall, we find how these two gases interact with each other. So, we will talk about one of the standard benchmark problems in the domain of shock tubes, which is called as the Swords shock tube problem test case 1, where what we have stated is that at time t equal to 0, we have two different states WL and WR existing across the physical wall. So, this is WL, this is WR, this is the wall or the diaphragm. So, in the literature it is more often referred as diaphragm, which are separating the two states. And in the left region we have a slightly higher density than the right state, and the gas is stagnant both in the left and right region because of the barrier, and the pressures is significantly larger on the left side compared to the right side, it is 10 times more. And you have to imagine that there are, in a physical setup, there have to be barriers at the end of the shock tube. You cannot have an infinitely long tube. So, you prepare a length which is suitable for your kind of work, and then once you are able to break the diaphragm at say t equal to 0 plus, you then see how the gases interact with each other. So, physical intuition will lead us to believe that the high pressure gas will rush into the low pressure gas, and that is precisely what happens. And then we can show that though initially the gases were stagnant, the moment they are allowed to interact, a very strong pressure wave percolates into the low pressure region, and that leads to the formation of a discontinuity, the shock. So, there is a normal shock which runs into the low pressure region, which is indicated by this green region. So, this is a shock, it is a normal shock, and it is a moving shock in terms of the laboratory frame of reference. So, if you are standing in the laboratory and you are looking at a shock tube equipments in front of you, then if you have some means by which you can either measure the movement of the shock or see it by some means, you will see the shock running away towards the right till it reaches the end of the shock tube there. Of course, once it reaches the end, it will reflect back and so on, but we are not going to go that far. We just look at the initial picture after the diaphragm has been ruptured, almost immediately after that. And then we find that as the shock runs away towards the right, it pulls with it the flow behind it, and somewhere in that flow there is also a contact discontinuity which is running behind the shock, and this contact discontinuity usually can sustain certain jumps across it. For example, entropy can change across this contact discontinuity, but you cannot have difference in pressure, for example. And then beyond that contact discontinuity, to the left end of the shock tube, you will find an expansion fan running away, which is shown through this region. Of course, as you can understand, all those lines are essentially characteristics, and this dotted line is the contact. So, you have the physical picture in the upper part of the diagram and the kind of wave diagram in the Tx plane or xt plane in the below diagram to understand or explain what the shock tube is all about. And we will try to see very soon that how pressure, velocity, speed of sound, density, entropy, Mach number, all these things would change over a very short time, given by t equal to 0.01 seconds after the diaphragm ruptures. So, we will discuss more about this in the next lecture. Thank you.